So guys, this unit, this chapter 16, 17 unit is going to take us well into March. And you're going to find over time, guys, that we have very few certainties as we start getting ready for the AP test. They don't tell us what labs to do, but we do know there will be a lab on the test. And guys, understand, I have no idea why, but chemistry is the only AP science class where they don't tell us what labs to do. In biology, Miss Harward has a list of labs she has to do. In physics, Josh, forget his last name, Kinney, has a list of labs he needs to do. Guys, in here, they say, here's 30 or 40 labs, pick the ones that you find most meaningful with your students. But then there's one on the test. And so we don't know what labs to do, but we know that there will be one on the test, and I'm pretty good at figuring out which ones to do. Guys, the only thing that we know for certain other than that about the test is that something from chapter 16 and 17 will be on the test. There will be an equilibrium problem on the test. Could be acid-base equilibria, could be solubility equilibria, could be gas equilibria, not exactly sure. But guys, there will be an equilibrium problem on the test. That's really the only other certainty we know. So guys, chapter 16 and 17 is a great way to end the year because we know we need to know it fresh because it'll be on the test. And it's just interesting chemistry stuff to know. Guys, what you're going to find out, again, is that this unit is enormous. It's 10 class periods. So, I mean, map that out over February and March, and we're not to spring break, but we're deep into March before we finish this unit. So, guys, this is actually really the last big unit that we're going to do this year. So, in many ways, as we wrap up this unit, when we hit the 10th day of this class, and it's actually going to be 11 days because we're not going to get done with everything today. So, guys, after we accomplish this, we get into this electrochemistry unit. It's actually 3 days long, including the test. We don't do oxidizing reducing agents anymore because they wrote it out of the test. So we do redox, we do batteries, we take the test. It's literally 3 class periods and we're done. So, because we're quickly, moving towards doing some last things. The other thing that you're going to see, just as we're thinking through where we're at relative to this, if my mouse will wake up, is, guys, the review books that I gave you. You don't need to bring them soon, but what you're going to see, and we're going to talk about this more later, probably right after we get back from President's Day, we are going to start reviewing for the AP test. Initially, that's going to take place outside of class. It's going to be additional things that you'll be doing at home. After spring break, we'll bring it in-house, and it'll be everything that we do for the rest of the year because we'll be done with all of that material that we just looked at. But guys, I know that you don't know the difference, but in my brain, today begins really that movement through spring and this important material and getting closer to us taking the AP test soon. So for me, this is it's a pivotal day. For you, again, it probably feels the same. But understand, guys, there are changes. Let me just tell you, you're going to see the homework load in this class is going to go up. Unapologetically, and not because I'm trying to just waste your time. But guys, this material is big and this material is important. And you know me well enough to know I'm not just going to give you busy work, but the reality of it is, guys, is to get good at this, there's a lot of material that you need to see and practice. And so, guys, you're going to see and it's not every night. Some of them are still going to be short and pretty quick. But guys, don't be surprised if a couple, maybe 2 or 3 times throughout this unit, you get a homework assignment and you're like, oh my gosh, that took me more than an hour. Don't be surprised by that because it is coming. So with all of that said, guys, that sort of sets the stage. I have a question for you. Do you guys all still have your test rewrites in your possession? Okay, you should. We're going to keep them today. We're going to talk about them on Wednesday. So I want to, so for now, just leave them. You don't need them. We're going to look at that on Wednesday. So guys, what we're going to do today is we're actually going to start chapter 16. So you're going to need note-taking materials, and that's it. You don't need a calculator. You don't need a periodic table. You just need note-taking materials. We're going to get started, but we're not going to get done, but we are going to get started. All right, let me get this finished printing. So guys, I didn't think this was humanly possible, but as a scientist collecting data, I think I may have actually gained more than 1 pound per day while I was on this trip. So my father-in-law, who's a business person, he's retired now, but the greatest joy in my father, we were down in Mexico with them, and one of the greatest joys in my father-in-law's life is finding a good deal. Right? I mean, this man will drive 30 miles to find like a Big Mac on sale at a McDonald's. Like, he just loves the deal. And we got down to Mexico, and we had already gone to Costco. We sort of gathered up some groceries. We were getting settled. And then when you get to the resort, he loves to sort of wander around and get a sense of what's going on. And he walks back into the room, and he's like, I think I found a deal. I'm like, oh, shoot. He's like, I think I found a deal. I'm like, all right, Jim, what's the deal? He said, I think we can get all-inclusive. Do you guys know about all-inclusive? It means you get this band and you can just eat and drink whatever you want, whenever you want, just full guns. He's like, I think we can get all-inclusive for $70 for the entire trip. And I'm like, oh, really? He's like, yeah, we're going to do this. We're $70, all we can eat. Let's $70. I'm like, I can't say no. I'm like, okay, let's do it. So it turns out, you guys know where this is headed, right? What did you have to do to get all-inclusive for $70? Timeshare presentation. Yeah, right? So the next thing I know, the next morning, I'm being whisked away with my wife by this bus, and we end up at some new timeshare property, and this lovely Mexican woman spent like 2 hours trying to convince us we're going to buy a timeshare. And I'm like, why would I buy a timeshare for you when I can come here for free with my in-laws? Do you see that this makes no sense? And literally by the time it was over, when we finally just looked her in the eye and we're like, no, we are not going, no. She started to cry. And I was like, oh, she's actually crying, like tears. And I'm like, oh no. But stood my ground, no, we're not. So then after that, they took us literally into a back room where they had another guy come and try to force us to buy something. And then when that didn't work, they took us into another room, and then they were going to give us the teacher discount on the timeshare. And I'm like, okay, this just has to end. So finally, we just got up and walked out. So I feel like I paid like $70 and a small portion of my soul anyway. So it was a week of just eating literally, I came back 6.5 pounds heavier than I left. So almost a pound a day. It was not good. But anyway, it was a lovely trip. So, oh, I know, right? But it was not good for my body. So with that said, guys, it comes as no surprise that what we're doing today is we're starting into a day of acids and bases. So guys, the date today is like the 9th, the 7th. Okay. So guys, let me explain to you how this is going to go. So chapter 16, you know from summarizing the chapter, it's foundational stuff. And guys, it's fascinating stuff. Today we're going to talk about acids and bases in ways that we never got to last year in general chemistry. So it's going to be super foundational, but it's also very, very interesting. Then what you're going to see is as we dig deeper into this, guys, we get to answer some really kind of, to me, interesting questions. We're going to answer this question, which you don't need to write down. But we're going to answer this question in the coming days. So, guys, we're going to answer this question. Oh, and actually, we can add another one. Let's do this. So, guys, we're going to spend an entire day and we're going to answer this question. Why is HF a weak acid? Why is CH3COOH a weak acid? Why is this a base? Why is this an alcohol? And why is HCl a strong acid? See, they all contain hydrogen, but why do they handle their hydrogen atoms so differently? Why does this give it away a little bit when this kind of looks like this? It's a hydrogen bonded to a halogen. So why does HCl deal with its hydrogen differently than HF? Then all of these contain OH. So why is this a weak acid? Why is this a strong base? And why is the last one an alcohol? See, guys, we get to answer all of these interesting questions. So chapter 16 is interesting, it's fundamental, it's foundational. We get into some really interesting stuff. Then, guys, 17, it becomes all mathematical. We're going to bring this icebox idea forward that you learned and took the test over just a couple days ago. And, guys, we're going to take this idea of equilibria and iceboxes, and we're going to apply it to acids and bases. And it's at that point that things get mathematically challenging, but they also get really interesting. We get to talk about buffers. We get to talk about all sorts of interesting stuff. So guys, you're going to find that this is by far my favorite unit of the year. It's interesting, it's challenging. We get the labs we do are great. We're going to titrate for days. But guys, you're going to find it's interesting stuff. But to get started, what we're going to do is we're going to start with some fundamentals. Now, here's what you're going to find. Guys, a lot of this is going to sound familiar, either from having learned it last year or potentially from having done the chapter summaries. So guys, what I'm going to encourage you to do is just write down the stuff you feel like you need to. But understand, you're going to see this is going to sort of sneak up on you. Because like, for example, what we're going to do is we're going to start by talking about definitions of acids and bases. And we're going to talk about the Arrhenius definition. And then we're going to talk about the Bronsted-Lowry definition. And some of you are going to be there like, wait a second, I already knew this stuff. Well, you do because you learned it last year. Doesn't mean you remember it, but you've at least heard of it. But then all of a sudden, we're going to dig deeper into it. So guys, I'm going to encourage you, if you're going to err on the side of writing stuff down, but also don't be surprised if you find yourself going, I kind of already knew this. So, for example, when we talk about acids and bases, guys, there's a couple different ways that we can describe acids and bases. The first way to describe acids and bases is under the Arrhenius definition of acids and bases. They're named after the chemists that came up with them. So guys, in the Arrhenius definitions of acids and bases, acids are simply substances that increase the hydrogen ion concentration when dissolved in water. Josh, do you get it now? Mass confusion. You okay? All right. Sometimes it's helpful to just give him some time. He just needs to reflect. It's getting better, though, as you think about it, right? Yeah.
Yeah.
No. Okay, no. Darn it. All right, so let's do bases. So guys, the definition of a base is a substance that increases the OH concentration when dissolved in water. So guys, now we need to ask the $10,000 question. Arrhenius came up with this idea like 150 years ago. The question is this: is it correct? Do acids increase the hydrogen ion concentration in water? They do. What about the base definition? Do bases increase the hydroxide ion concentration in water? Also, yes. Guys, this definition is actually very useful to us. It's not wrong. But guys, the trick is that it can be self-limiting. Let me show you what I'm talking about. So guys, for example, and maybe it would be worth remembering this. Guys, sodium hydroxide, strong base, right? So what does sodium hydroxide do in water? Well, guys, when we put sodium hydroxide in water, it is also a strong electrolyte, and it does this. So connect that to the Arrhenius definition of a base. So sodium hydroxide is a strong base. You know that because you memorized them. Because now would be a good time to go back and refamiliarize yourself with the strong acids and strong bases. Maybe we should remind ourselves quickly. Guys, which are the strong bases? Do you remember? So these dudes, and then heavy these dudes, right? So lithium. We don't count francium because it's super radioactive, and then calcium down to barium, and then also we don't count radium because, again, radioactive. So it's basically the hydroxide salts of those dudes. Is that okay? So sodium, of course, is one of them. Sodium hydroxide, you dump it in water, it dissolves into sodiums and hydroxides, and now we have an increase of hydroxide ion concentration in water, and that makes sense, and we get the idea. Good? Okay, but then guys, what about this? NH3. Is NH3 a strong base? No, it's not a hydroxide salt of group 1 or heavy group 2. But guys, it is a base. But there doesn't appear to be a place in the Arrhenius definition to explain why it's a base. So guys, what we're going to do is we're going to bring the Bronsted-Lowry understanding of acids and bases into this, and we're going to see that NH3, ammonia, fits really neatly into the Bronsted-Lowry definition, but then we can cycle that backwards and find out that it doesn't violate Arrhenius. So guys, what is the difference between the Arrhenius and the Bronsted-Lowry definition? Well, let's talk about it. So guys, the Bronsted-Lowry definition of an acid, it seems really simple, and it is, but there's a lot going on here. In the Bronsted-Lowry definition, an acid is a proton donor. And a base is a proton acceptor. So guys, what I want you to do is connect the Bronsted-Lowry definition with the Arrhenius definition. So connect this with this, connect this with this, and then what I'd like you to do is think about, let's do strong right now. And I'm not going to complete that one for you. So guys, what I want you to do is I want you to first of all make the connections. There are strong and interesting connections between the Bronsted-Lowry definitions of acids and bases and the Arrhenius definitions of acids and bases. So connect acid to acid and base to base, and then talk about how this meets both definitions qualifications for an acid, and then if you're feeling brave, figure out how this meets the definition of a base in both definitions. So guys, we're going to take this in pieces. Acids first. How are the Arrhenius and Bronsted-Lowry definitions of acids the same? Talk to the person next to you. Got about another 10 seconds, y'all. Okay, so let's pull that one together. And guys, I love eavesdropping, and I think you're on it. So now let's go to the next one, and we're going to come back and talk about them, but I want you to process first. So guys, bases. How are these? This one's trickier. How are these connected? Arrhenius and Bronsted-Lowry bases. Talk about that. How are those connected? So guys, can we wrap up that conversation briefly? So I want to talk with you about those ideas that you were just discussing before we then chew on these other ideas about how the stuff that remains on the board fits the descriptions. So guys, let's do this one first. So acid to acid. And we were talking a moment ago about the idea that there's a connection between the Bronsted-Lowry and the Arrhenius definition of an acid. What's the connection? You guys all talked about it. Go ahead, Isaac.
The H plus is literally just proton.
That's it. Guys, if you don't see that connection, I would literally encourage you. Oh shoot, I didn't want to do that. Let me erase this. Guys, I would literally encourage you to write this down. So what's the connection here? H plus equals proton. Sorry that's so messy. I had a hard time doing that. But guys, not conceptually, it's the case. Hydrogen ions are protons. Yeah. There isn't. It's just a different term to describe the same thing. And if you're not clear why, let's just do this quickly. So 1 proton, 0 neutrons, and 1 electron, right? So that's a hydrogen atom, 1 proton, no neutrons, 1 electron. So that's a hydrogen atom. But if we make this a hydrogen ion, we take away the electron. So what's left? A proton. So literally a hydrogen ion is a proton. And so we can use either term. And actually, Chase, it's good you asked that. We will use those terms interchangeably. We will say acids give away hydrogen ions. You bet they do. Acids give away protons. You bet they do. If we use them interchangeably, they're the same thing. So hydrogen ions are protons. You guys okay on that idea? Hydrogen ions are protons? Okay, so guys, let me do this then. Don't miss this. We're going to prime the pump a little bit for the second conversation. So, no, we're not. We're going to, actually no, because it's going to give away too much. So guys, let's talk about the second idea then, that bases are also similar if we can unpack the complexities of these definitions. Because guys, Arrhenius and Bronsted-Lowry are also functionally saying the same thing. Did you figure out the connection? Go ahead, Maddie. Yes.
So ammonia, it would take a hydrogen ion, right, to become ammonium. The hydrogen ion, where does it come from? It comes from the water, which creates hydrogen.
Okay, so guys, stop right there. That's the critical connecting point. And I was actually thinking about getting rid of the ammonia because I didn't want it to become our focal point, but we need a focal point, right? So guys, this is the fundamental understanding that you've got to have. And this is weird and this is different, and frankly, don't miss this because it's part of what makes acid-base chemistry frankly difficult. Guys, when we talk about acid-base chemistry, where does all this chemistry take place? In water. And guys, here's the deal. The water is not passive. Imagine if you've got kids playing on a playground. Can you picture it? Guys, if kids are playing on a playground, the playground is passive. The playground is just a place where the kids come to play. Guys, that is not what's going on in acid-base chemistry. When you do acid-base chemistry, the playground is water. But the difference is the playground is actively involved in the game, which could be an amazing like sci-fi fantasy. I mean, imagine kids out playing on a playground and the playground comes to life and gets involved in the game. Guys, that's what we're talking about here. All of this acid-base chemistry happens in water. But guys, we live in this amazing universe where water, ready for this? Water is both an acid and a base. You're going, wait, what? I thought water was H2O. Well, guys, water is H2O. But if we draw it like this, maybe it's easier to see that water has hydrogen. And that makes it an acid. But water also has OH, and that makes it a base. Now, guys, where you choose to go with this is up to you. But to me, that doesn't seem coincidental. That we live in a world where the most plentiful substance on earth happens to be the most simple example of an acid and a base simultaneously providing the perfect environment in which acid-base chemistry can take place. And guys, the chemistry of life is acid-base chemistry. The code that makes up who we are is DNA, which is deoxyribonucleic acid. See, guys, to me this is and sorry if this seems weird, but to me this is bordering on spiritual. Because we live in a world where the most plentiful, the most fundamental, the most critical, it's water. And water is perfectly an acid and perfectly a base. It's perfectly both. And so, guys, when we think about and when we talk about acid-base chemistry, we've got to understand that this is always in the context of water, but water is no longer the playground where things just come to play. Water becomes an active participant in the chemistry itself. So guys, now that we understand that, we can now take this idea. So let's do this. Arrhenius definition. What do bases do? Just read it. In the Arrhenius definition, what do bases do? They make OH go up. But guys, check it out. In the Bronsted-Lowry definition, it's saying exactly the same thing. And let me show you how. So guys, let's go over here to our picture of a water molecule. And then let's say, for example, here we have a base. But this is a Bronsted-Lowry base. What does Bronsted-Lowry say bases do? Accept protons. Oh, look, there's a proton. So this base is going to accept a proton. You'll find out later we call that HB, and then it would have a positive charge because the proton's positive. So what we've just said is that the base accepts a proton from water, and all of this chemistry happens in water. But if this is now gone, what's left? OH. And what does that make the concentration of OH do? Go up. And now all of a sudden we have the Arrhenius definition. Do you see the connections? So guys, let's make sure you're clear on that. When you come back over here, what is the connection between this definition and this definition? And the connection is water. This chemistry happens in water. And as a base takes in an OA, or takes in a hydrogen, a proton, a hydrogen ion, as a base takes in a hydrogen ion from water, we're left with OHs, and all of a sudden the OH the concentration goes up, and now we're back to Arrhenius. Do you see those connections? So guys, let's now answer the question that we talked about a second ago. If this is all true, then how do we make this connection? So HCl, does it fit the Arrhenius definition of an acid? Well, absolutely, because it's giving away hydrogen ions, but do you see that it's also donating protons, which are hydrogen ions, and now they connect? Well, what about the water? What about this idea that this happens in water? Well, guys, the answer is this. Where does HCl do this chemistry? In water. We're talking about HCl breaking apart into hydrogen ions and chloride ions, and that happens in water. So this happens when this stuff goes into water. It releases hydrogen ions, the concentration goes up, but that's the same as donating protons, because as Chase pointed out, hydrogen ions and protons are the same thing. You guys good? So then we come back to this idea, okay, well, what about bases? So guys, how does NH3 meet both of these definitions? Well, here we have to remember that this is happening in water. And when it does, if NH3 is a base, what's it going to do? What does NH3 do if it's a base? It takes in a proton from where? From the water. Well, that makes NH4, and if we now have NH4, what's left over? OH, and guys, that then meets both of these definitions. Did this increase OH concentration? Yes. Did it accept a proton? Yes. And so now all of a sudden, guys, we see that these definitions fit together. Questions or things there that you want to talk about? Yeah.
When did this definition happen? Like, what time finish?
I got to be really, I would guess 1850s and 1870s, 80s? Do you guys know? Does it say in the, I'm guessing. To me,
I just want to know if they were like relatively close to each other or like 100 years.
So Kaylee, do you have the answer? 1923? Oh, snap. Yeah, so Bronsted and Lowry didn't know each other, but they both got credit for it. So that's weird. 100 years ago, so 1880s. So I was off by 50 years in both cases. So 1880s and 1920. That can't be. I mean, it is. But in 1920, we were just discovering fundamental things about acids. That's weird. That's weird. Okay. So, guys, let's do this then. Which of these definitions then are we going to use? Well, guys, we understand that fundamentally they're the same, right? But here's the deal. We are actually going to live in the Bronsted-Lowry context when we think about acids and bases. The reason is this. Guys, technically, and be careful with this, acid-base chemistry doesn't have to happen in water. We're not going to talk about acid-base chemistry that isn't aqueous chemistry, but technically it doesn't have to happen in water. All that you need in the Bronsted-Lowry sense in order to have an acid-base reaction is something that gives away a proton and something that takes in a proton. And so guys, for this class, for our purposes, we're going to live Bronsted-Lowry. Now understand, there's even a third definition of acids and bases. Did you run into it in the reading? What is it? It's the Lewis definition. The same guy that was the electron fanatic that did Lewis dot structures. Guys, there's another definition for acids and bases. It's the Lewis definition. You will not get into that until you get into organic chemistry your sophomore or junior year, where you start doing what are called electron pushing diagrams. So the difference is that Bronsted-Lowry focuses on the protons. Lewis focuses on the electrons. Guys, we will talk about it in a couple days. There's a couple multiple choice questions on the test about it. So we'll cover it enough that it's not unfamiliar, but understand you're going to do a lot of it when you get into OChem, probably your sophomore year in college. So there is a third definition, but again, guys, this is where we're going to spend our time. Is that good? Okay, so I think I'm just going to skip to the next. Yeah, we're just going to skip from there. Well, okay, we'll click through them. So the idea then, guys, is that the majority of, well, for our foundations, we're going to use the Bronsted-Lowry definition. But what we need to do now is we need to better understand what acids specifically do in water. Now, guys, you've already learned about this, but let's write down what you need just to remind yourselves. Do you guys remember hydronium ion? Do you remember that critter? By the way, guys, too, it is one of the ions that you needed to memorize. If you're starting to think, you should be starting to think about what are things you could be doing now to get ready for the test in May. Guys, one of the things that you could be doing is starting to review the stuff you did for the summer quiz. Memorizing your ions, memorizing your solubility rules, rememorizing your solubility rules, going back over the strong acid-base formulas, things like that. But guys, one of the polyatomics that you should have learned was hydronium ion. So guys, where does hydronium ion come from? And the answer is acids in water. So when you put an acid in water, and we're going to use the Bronsted-Lowry definition, guys, when we put acids in water, these things give away hydrogen ions. When they do, they react with the water to form hydronium ion. Oh yeah. So guys, if you don't want to write out the Lewis dot structures, you could just do hydrogen ion plus water yields hydronium ion. So guys, this is actually what acids do in water. Technically, acids do not just dissolve in water, they actually react with the water. So when you dissolve an acid in water, don't think about the dissolving video where the water molecules are surrounding the ions. That's the wrong picture. When you dissolve an acid in water, the acid gives away protons. These protons literally grab a hold of two of those electrons and they create a third covalent bond, and you end up with hydronium ion forming. And guys, the trick is this. All acids give away hydrogen ion, so all acids form hydronium ion. That's what acids do in water. If you didn't know that, or that's not a part of your understanding, you may want to scratch that down. Guys, the idea is that hydronium ion is the substance that gives acids their characteristic properties, because all acids form hydronium ion in solution. So why are some acids really dangerous, and why are some acids like vinegar delicious on salads? The amount of hydronium ion they form. The more hydronium ion they form, the more reactive they are, the more dangerous they are, if you will. But it's all about hydronium ion. Now guys, this brings us to an interesting point, and this is going to be important, so don't miss this. Guys, a minute ago, Chase mentioned this idea, and he said, which one is it? What are we going to call this? So guys, what is that? Hydrogen ion, or a hydrogen ion is a proton. So guys, we can call that a hydrogen ion, or we can call it a proton. Now guys, let's be clear. This hydrogen ion or proton does not hang out by itself. It will always grab a hold of two of those electrons, and it will always form hydronium ion. So guys, if you have an acid, there is no free hydrogen ion. There are no free protons. These protons always grab a hold of water, and they always form hydronium ion. So if you put HCl in water, there's none of this. All of this gets converted to that. Does that make sense? So guys, here's what that means. That gives us some choices. That means that we can represent hydronium ion in two different ways. You're going to want to write this down. We can represent hydronium ion as just H+. Or we can represent what it actually is, which is H3O plus. But guys, the thing you've got to get accustomed to is that these are used interchangeably. So let's pause and make sure you're clear. What is it that allows us to do this interchangeably? Why is it that we can either say acids produce hydrogen ion, or we could say an acid produces hydronium ion, and either one is fine? Yeah. Because it's always in water. So guys, the idea is this. If you're not catching on to what we're talking about, imagine that we have HCl. Here's an example of what we're talking about. And when we talk about the chemistry of HCl, we could say that HCl breaks apart into hydrogen ion, protons, and chloride. Is that true? Absolutely. But guys, where does that take place? In water. So we could come along and say, okay, well, if that happens in water, let's include the water. Well, when we include the water, now we get this. So which one is correct? Well, both of them. This is just abbreviated, if you will, because we're not including the water. But guys, we know the water is always present, and because the water is always present, many times we won't write it like this because we understand that it always happens in water, so we'll just say hydrochloric acid breaks into hydrogen ion and chloride ion, but we really understand it's happening in water, and the chemistry that's really happening is this, and the hydrogen ion grabs a hold of water and forms hydronium. As a result, we can write it in either one of these ways, and you'll get good at choosing. Sometimes we need to include the water, sometimes we don't, and then we just write hydrogen ion. Is that okay? All right. So, guys, this is where we are right now. We've talked about the definitions of acids. We've learned that they're similar. There are some differences. That Arrhenius always has to be in water. Bronsted-Lowry not necessarily, but we're going to understand that it's in water anyway. And we understand that acids give away protons and bases take them in, because we're going to talk Bronsted-Lowry. You guys good to there? Anything you want to talk about? You guys good? Okay. So, with that said, do you remember conjugates? Guys, remember conjugates? If you don't, let's go over them quickly. So guys, here's the deal. Last year, conjugate acid-base chemistry for you guys was an end unto itself. You were given balanced equations and you had to find which one's the acid, which one's the base, which ones are the conjugates. Do you remember that? Guys, now, especially in chapter 17, we are going to talk more about the chemistry of conjugates than we are about the chemistry of the original acids and bases. Conjugate chemistry is going to become critical. We're going to talk a lot. So guys, right now, all that you need to be able to connect with is what conjugates are. So guys, when we talk about conjugate, we mean to change into something new. Like when you conjugate verbs in Spanish or French, you've got your IR verbs and your AR verbs and your ER verbs and voy, vas, va, vamos, van, and all of that good stuff. But what you're doing is you're taking verbs and changing. To conjugate means to change. Well, guys, that's what we're doing here. When an acid and base react, they are forming a new acid and a new base, and we call these things the conjugates. Now guys, when we do that, the fundamental chemistry looks like this. An acid and a base form a conjugate acid and a conjugate base. So guys, do you remember? it's up to you. This is stuff that you learned last year, but if you think it would be worth having the muscle memory experience of writing it down, I'll go slow enough that you can. So let's remind ourselves, guys. So what is a conjugate acid? A conjugate acid is the particle that's formed when a base accepts the proton. Now, guys, even if you're not writing that down, please let that be more than just words to you. What do bases do? Well, bases are proton acceptors. So when a base accepts a proton, it now has a proton, a hydrogen ion, that it didn't have before. So now that base, with its extra hydrogen, can now function as an acid and give that hydrogen back. So picture base, takes in a hydrogen, now it's got the hydrogen, it could give it back, and when it gives it back, it's now functioning as an acid. So guys, fundamentally we say this, base plus the proton, hydrogen ion, gives us the conjugate acid. Too fast, too slow. Just right. So guys, I'm assuming then from that you could probably derive a conjugate base. A conjugate base is the particle, well here, it's the particle that is formed when the acid loses a proton. Can you picture that one too? You're an acid, you lose your proton, now you're missing a proton, you'd like to have that proton back, and when you grab that proton back, you're now functioning as a base? Does that sort of jive? So what we say then is this, an acid minus the proton, the hydrogen ion, gives us the conjugate base. How we doing? You okay? Okay. Guys okay? So guys, let's do this then. I'm going to go to a clean screen, but what I want to do is I want us together to write out some of this chemistry and get a sense of what this actually looks like. So let's do a strong acid first. Nitric? What's nitric acid? HNO3. If you don't know that, guys, that should be a real key indication to you that you need to start right now, not later, right now. Like, guys, I would go back and get that summer assignment, and somewhere I would make it a part of your world. If you spend time memorizing other things, I think probably many of you memorize scripture and things like that. Not that this is any way equivalent to that, but if you have memorization systems in place in your world, add this to it. Guys, you got to start reconnecting with these. So let's take, for example, HNO3, which is nitric acid. Now, guys, please don't write this down, but watch. What we could do is this. We could say that nitric acid does this, and that would be this breaking apart. But again, guys, where does this happen? In water. So let's include the water. So now we're going to go, and this you do want to do with me. Let's include the water. So now write the products. You should be able to do that. What does this produce? So guys, let's talk. What does nitric acid do? Because it's an acid. Gives away hydrogen. Where does it go? To the water, right? So the water picks up the hydrogen ion. What does that turn water into? Hydronium ion. And so guys, it goes like this. So the water picks up the hydrogen, and then the nitrate gets the bootski, and it looks like this. Yes? Okay, so now guys, let's do this. Acids bases, conjugates. Please, and I'd like you to commit to an answer. Please, underneath these four, and we're going to say the conjugates are on the right. Those are what were formed. And the original acid and base are on the left. Guys, please, underneath these, write an A for acid, a B for base, Ca for conjugate acid, and Cb, of course, for conjugate base. Please label these. So if you're stuck, if you're frozen, if you're not doing it, guys, do it. You got to get over this habit of when it's time to answer a question, freeze. It's got to be time to answer a question, do. You don't want to train yourself to freeze. So guys, you should be done. If you know what you're talking about, please share what you did with the person next to you and come to consensus. Okay, guys, let me pull this together. Here we go. So, guys, there's 1,000 things that we can and eventually will talk about. There will be some review along the way, but let's do this first. You ready? Earth-shattering idea. Nitric acid is an acid. I know it's true. And so, guys, if nitric acid is the acid, of course, that then makes water the base. But some of you may be thinking, wait a minute, can't water also be an acid? And the answer is yes. And what is the name that we give to a substance that can be either acidic or basic? Amphoteric. We'll come back to it later. Don't write it down now, but water can be both. Now, guys, what if you were given this and you forgot that HNO3 is an acid? How do you know? And guys, what we do is a process of comparison. So say, for example, which one's the acid? What we would do is we would go to one of the substances and take a hydrogen away. That's what acids do. Look for the acids. Take a hydrogen away and then look for the remnants. So guys, if you were to take a hydrogen off of water, what would be left? OH. But we don't see any OH over here. So that tells us that's not what this chemistry is doing. So then we can come over here and we can take the H away, and the remnant is nitrate, and we find that telling us that this is the thing functioning as the acid. Does that make sense? Okay, now, because now we need to find our conjugates, and the easiest way to do it is go to the acid and take away the hydrogen. Whatever is left is the conjugate opposite. That's the conjugate base. If you didn't know that or you got it wrong, fix it now. Then the other thing that remains is the conjugate acid. Is that okay? Okay. So guys, if that's okay, I would like you to please do that same process with vinegar and water. Predict the products, and then identify them as acids, bases, and conjugates. You guys okay? Oh, my trash can went away. All right. So, guys, starting then from the top, you should know that vinegar is acetic acid, which is an acid. Now, that probably brought you to a question. We'll talk about it now, but we'll further define it later. Which hydrogen comes off of vinegar? And guys, the answer is the last one and not one of the hydrogens bonded to the carbon. Why? We'll talk later. For now, what you need to know is that when we write the chemical formulas for acids, there will always be a lone hydrogen. It will either be very last or very first. That is what is called the acidic hydrogen. So the hydrogen that comes off is the last guy. Now, where does that hydrogen go? To the water. So it forms H3O plus, and then the thing that remains is the acetate ion. Again, if you didn't know that was acetate, you've got work to do. Okay, so now guys, we need acids, bases, and conjugates. I think we can say with certainty that this is our acid and this is our base. Then to do our conjugates, we're going to cover over the hydrogen. What's left is the conjugate base, making the other the conjugate acid. Are we good? You okay? Okay, now guys, I know the day's been a little long. I know this has been dense, heavy stuff. Do not miss the next 3 minutes. Here's the question. That second one is wrong. Why is it wrong? Good. Vinegar is a weak acid. So what can we do to correct the equation? Yeah, we need an equilibrium arrow. Now, guys, do this with me. This is strong. This is weak. HNO3 is a strong acid. Vinegar is a weak acid. We represent that by either a single-headed arrow going to completion, quantitative chemistry, or a double-headed arrow signifying equilibrium. Here's the question you've got to understand the answer to. Why? Why is HNO3 a strong acid? And why is vinegar a weak acid? And guys, I ask the question somewhat rhetorically. I fear that if I allow you to guess at this, it could get so sloppy, you're going to miss the answer. So I'm just going to tell you, why is nitric acid a strong acid and why is vinegar a weak acid? And guys, the answer is this. Do this with me. Nitrate is a worthless base. Acetate ion is a strongish base. Not strong, but strongish. So guys, this is the idea. We're going to start by talking about the first reaction. Why is nitric acid a strong acid? And it has nothing to do with the nitric acid. It has to do with the nitrate. So here's what happens. This acid gives its proton to water. And water goes, hey, I'll take that. And it turns into hydronium ion. And then the other thing that's produced is nitrate. But nitrate is a worthless base. Nitrate does not have the ability to take the proton back from the water, so nitrate just hangs out on its own. It never steals the proton back, so the reaction never goes in the other direction. So guys, what's the big idea? What makes a strong acid strong And the answer is they all have worthless conjugate bases. If you need to, write that down. What makes a strong acid strong? They all have worthless conjugate bases. Go ahead. No. Chase, I love where you're going with that. Chase's question was, does this relate to electronegativity? And the answer is no. But it does relate to stability. So let's talk about this. Ready? Solubility rules. Solubility rules. What do you know about the solubility of all the nitrates? All nitrates dissolve in water. Why do all nitrates dissolve in water? Because nitrate is amazingly stable. What makes it stable? Resonance, it's delocalized pi bonding. It resonates. They're all connected. But the big idea is this. Nitrate is amazingly stable on its own. So not only does nitrate not want to undissolve, nitrate also doesn't want to grab hydrogens back. And as a result, nitrate doesn't grab these back, and so it doesn't go in the other direction. So it's not electronegativity, but it is stability. Brescia, go ahead. Are you sure? Okay, yeah.
How do you know what stability is?
And that's the point. You don't need to know. What you do know is this. Cl Bri NO3 SO4 2 minus ClO3 minus and ClO4 minus are all worthless bases. How do I know? Because if I put hydrogens on these, I just got the 7 strong acids. So the idea is that all of the strong acids have worthless conjugate bases. And those are the only worthless conjugate bases. Is that okay? Is that okay? Well, be careful, because those are the only, yes, they would be. There are other ions that don't move in the other direction, but then it's not acid-base chemistry. Yeah. Do you get the idea there, Santiago, please? Yes. Yeah, so HF, right, isn't on the list. So that means that when HF forms this, the fluoride goes, hey, I'll take my hydrogen back, right? And the fluoride will take the hydrogen back and push the reaction in the other direction. That's a great observation. But now, Chase, here's where we've got to be careful, right? Because you ask, is it about electronegativity? And the answer was no. We said it is about stability. And then we link stability to solubility. That breaks down here. Because all acetates also dissolve in water. But now we've got an ion. Guys, we're now moving down to vinegar. Now we've got an ion that does go the other direction. So here's vinegar. Vinegar goes, hey, yo, I'm going to throw my proton over there to water. Water goes, I got you. I'll take that. And that forms hydronium ion. But then these acetate ions go, gosh, I really kind of miss my hydrogen. I'd sure like to get my hydrogen back. And so the acetate goes over here and goes, hey, can I have my hydrogen back? And it turns out that acetate is a strong enough base that it can take its hydrogen back, and it takes the hydrogen back from the hydronium, and it drives the reaction in the other direction, making acetic acid weak. Do you see how that works? So it's not directly connected to solubility, because if it was, both of these always form soluble salts, so they should behave the same here too, and they don't. So it is more complicated than that. But understand the difference here, guys, is that acetate is a functional base. We call it strongish. And so acetate has the ability to steal the hydrogen back, and as a result, this reaches equilibrium, making acetic acid weak. So what have we just said? And the answer is this. Strong acids have worthless conjugate bases. Weak acids have conjugate bases that actually function as bases. They're not strong, but they're not worthless. They're strongish. Do you get the idea? Now, guys, we need to replace the term. We don't say worthless base. Don't do that on the test. It's probably some unpolitical correct. We don't call things worthless. You'll probably get canceled in our culture. Don't call it worthless. The word that we use is of negligible strength. So if you ever have somebody come to you and say, you're worthless, you just say, no, I'm just of negligible strength. Okay, that's sad. Never mind. I pray that doesn't happen to any of you. But guys, it's not worthless. It's of negligible strength. So now, guys, let's do one more. Don't write this down, just watch, and we're going to wrap this up. Santiago, I want to talk about your example. You brought up HF. Sorry this is so low on the board, but can y'all see it? Is that okay? So, guys, HF is a weak acid. So what do we now know about fluoride? Is it a worthless conjugate base? No. So it is strongish. But here's the trick, guys. Strongish isn't always the same. Guys, it turns out, ready? This is deep. It turns out that hydrofluoric acid is a stronger weak acid than vinegar. Hydrofluoric, they're not strong. They don't go to completion. But hydrofluoric acid is a stronger weak acid than vinegar. Did you hear that? This is stronger. What does that mean? It means that this is weaker than this. Let that soak in. HF is a stronger weak base, so fluoride is a weaker, HF is a weaker strong acid. HF is a stronger strong acid, my bad. HF is stronger. Let's do this. Don't put this on your salad. Vinegar, yummy. Hydrofluoric acid, not good. It is weak, but it's still really, it makes a lot of protons. So guys, this is a stronger weak acid, so this is a weaker weak base. Do you kind of get that? The idea is this. HF gives away a bunch of hydrogens to water, makes a bunch of this, and fluoride's over here going, I might take a couple of those back, but I don't want a lot of it back. And because this is a weaker weak base, it doesn't drive the reaction that direction so much, and it makes the HF stronger. So just a second, here's the relationship. The stronger the acid, the weaker the conjugate base. Does that make sense? The stronger the acid, the weaker the conjugate base. The stronger the acid, the weaker the conjugate base. And guys, that goes all the way to the extreme where we have an acid that is strong. And a strong acid has a conjugate base that's so weak, it's worthless, of negligible strength. So the stronger the acid, the weaker the conjugate base, all the way to fully strong and fully worthless. Go ahead. Say that again. And that's where we're going in chapter 17. What we're going to do in chapter 17 is we're going to quantify this, and we're going to write Kc values for these things, talking about where the equilibrium lies as a representation of the strength of the acid in the conjugate base. They're actually called Ka values, and that's exactly where we're going. Yeah? Correct. And by definition, remember when you don't remember, this was September. When we defined strong, we didn't mean strong like strong. In chemistry, strong just means complete. And so this completely turns into hydronium ion. That's strong. Only 7 acids do that. These are weak, and what that means is they don't go to completion. They don't fully protonate. But understand, HF is terrifying. If you've watched, what's the drug dealer chemistry movie? Breaking Bad. If you've watched Breaking Bad, this is the acid that Walter had his little buddy dump the dude in to dissolve his body after they killed him, and it burned through the bath. You guys watch Breaking Bad? Don't watch Breaking Bad. It's horrible. HF is terrifying. It's a weak acid, but it's a terrifying acid. So understand, okay, that strong just means complete, weak just means not complete, but you can have really terrifying weak acids. But guys, importantly, do you see the connection between the strength of the acid and the conjugate? Okay. So with that said, y'all, I know that in the past we've kind of said, hey, we didn't get done. Do the homework as you want. Nudge, nudge, wink, wink. Get done what you can. Well, guys, yeah, I mean it. You want to get as much of this done as you can. I warned you up front. Homework's going to pick up. So guys, you will not be able to do all of this, but we're going to grade homework now. We can't. Shoot. It's Wednesday, short day. Thank goodness we have a school board that actually understands what teaching looks like. Oh, wait. Makes me want to go to the Lehigh Free Press. So guys, do what of this you can. And at some point it has to be me not arm twisting. It has to be you engaging and caring. Do what of this you can. It'll be foundational to what we're doing moving forward. And we're going to stop there. Let's take a break and we're going to come back into lab in third period.